Hey folks, in this video we're going to be talking specifically about Half-Life. So let's get going. Wow, really excited about these objectives. Anyway, I want you to explain what Half-Life is in the context of nuclear chemistry, explain how the half-life of an isotope relates to the stability of the isotope, and perform calculations using Half-Life, which I'm really excited about. Anyway, Waffles? I don't know. Let's get going. So Half-Life, which we're going to represent with the symbol T with a little 1/2 down there, and this is the amount of time it takes for half of the atoms in a sample to decay. And by decay, I mean break apart into something else. So we no longer consider them to be the same atom. So as I said, T with a little 1/2 is our symbol for half-life. And we're going to measure this in units of time. And so this can be really, really short, from less than a second to super long, way, way, way big, trillions of years. Each different isotope has its own unique half-life. And so this is kind of an indicator of its stability. If it has a very long half-life, well, that means it's going to sit around for a long time, and that's pretty stable. If something sits around and doesn't change for a very long time, it's pretty stable. If it reacts in the blink of an eye, I would say that it's very unstable because it didn't last very long. So examples, because examples help. Let's say we have 4 radioactives, and the half-life for this isotope is 10 minutes. Well, here are my 4 radioactive elements, or atoms, and after 10 minutes, half of those dudes are going to decay, and they're going to decay into something else. So I'm not going to totally take them off the table, but they're something else now. They're not the element that we're studying. And so after another 10 minutes, half of my sample will decay. So I only have 1 atom left. Usually we're not thinking about 1 atom, and I'm not going to include what goes on after this because honestly, it might decay and it might not. But we're going to usually deal with tootloads of atoms because that's how chemistry is done. You generally have tootloads of atoms, not 1 at a time, unless you're a baller. Anyway, every 10 minutes, we have half of our radioactive atoms decaying. And so the decay products, these actually might be radioactive and decay again, but as I said, we're not going to worry too much about those. So let's do some half-life maths. We know that the half-life tells us how long it takes for half of a sample to decay. So we're going to use this to figure out half-life problems. So most of these problems are going to involve us multiplying 2 by 2 or dividing by 2 a bunch. And because, as I said, every time a half-life passes, the amount of atoms are halved or divided by 2. So we're going to use that to help us work our way through these problems. So let's say an example. We got 78 grams of an isotope. We know the half-life is 10 seconds. How many grams will be left after 40 seconds? All right, well, pause the video and think about that. Okay, cool. So we know the half-life is going to go by 40 times. No, 40 times? The half-life is 10 seconds, so 4 half-lives is 40 seconds. So that means this dude's going to get chopped in half 1, 2, 3, 4 times if 4 half-lives go by. So my starting mass, I know 78 grams. My ending mass, I don't know. I know the half-life, again, is 10 seconds. The total time is 40 seconds. So from this, I can figure out how many half-lives went by. And that's really going to be our jumping off point for all of these problems. The first thing we want to do is figure out how many half-lives went by. So we know 4 half-lives went by, as I said. And so we can take our 78 grams and cut that in half 4 times. In 10 seconds, we'll chop it in half. In another 10 seconds, we'll chop it in half. In another 10 seconds, we'll chop it in half. And then in the last, making 40 seconds, we chop it in half 1 last time. So that is how we solve that problem. Nifty. Cool. Well, let's look at another guy. We got some lithium-8. We know its half-life is this minuscule 0.838 seconds. We know that after 4.19 seconds, we find we have 10 grams of lithium. How much did we start with? Okay, so let's do a little inventory. We don't know the starting mass. We know the ending mass. We know the half-life, and we know how much time total has gone by. So first thing we want to do is figure out how many half-lives went by, because that's always what we want to do. How many half-lives? We'll divide the total by what the amount of time is for 1 half-life. So we can do that maths, and we got 5. So we know that 5 half-lives are going to go by 5. So we know that whatever our starting mass was, that guy got cut in half 5 times to give us 10. So we'll do the reverse. We'll take 10 and we'll double it 5 times. So 10 doubled. If we go backwards in time, it would be 20. If we go backwards in time again, it would be 40. If we go backwards in time again, it would be 80. Backwards in time again, 160. Backwards in time again, 320. And that was, we doubled it 1, 2, 3, 4, 5 times. Good. Cool beans. So we know that we should have started with 320 grams of this lithium-8. Nifty, nifty. Let's look at some waffles. Oh, those are some tasty looking waffles. Oh, yeah, I want to eat those waffles. 30 ways to eat waffles for every meal. Yes, but no, I don't think I condone that. That seems wrong to me. No. So anyway, I don't know what that waffle shtick was. Let's do another problem. Let's see what's going on here. So, what? All right, you've got a half-life. Let's do our inventory. All right, we know our starting mass. It's this many grams. Okay. We know our ending mass. It's this many grams. Okay, cool beans. We got that. We know the half-life. Okay, cool beans. And we don't know the total time. That would, I guess, would be how long we can hold our breath. So we need to figure out how many half-lives went by. So what we can do, since we don't know that from half-life and total time, is we can use our starting mass and our ending mass and figure out how many half-lives went by. We can just start with our starting mass and cut that in half until we get to 7. Or we could go the other way and double this until we get to 56. But I'll start with 56 and I'll cut that in half. And I'll say, okay, that's going to be 0.0028 grams. And I'll take a note of how much time went by. And I'll cut it in half again. And I'll cut it in half again. Oh, cool. And now we're at our 0.0007. So I know that 1, 2, 3 half-lives went by, or 55.6 seconds times 3, giving me a total of 166.8 seconds. Apparently, you can hold your breath for 166.8 seconds. That's a really long time. That's almost 3 minutes. Nice. Good for you. Let's do, I don't know, another rhyming half thing? I don't know what's going on up there. Let's try this problem. Pause the video and give this dude a shot. All right, let's go through it together. All right, so we know our starting mass. It looks like we know our ending mass, and I guess this is total time because we're being asked what the half-life is. All right, so we got starting mass, we got ending mass. We don't know what the half-life is, but we know the total time. Well, in order to figure this out, guess what we're going to have to do? Figure out how many half-lives went by. And I guess we're going to have to use our two masses because we don't have both of these guys. So we'll take 128, I'll chop it in half, I'll chop it in half, I'll chop it in half, I'll chop it in half. Now I'm at 16. I know 3 half-lives went by. Sick. So I know that in this amount of total time, 3 half-lives went by. So I can divide my total time by 3 to get 425.7 years of my half-life. Cool beans! All right, well, that's the end of this video. I hope you feel cool about doing math with those half-lives. Remember, get the number of half-lives that went by first, and then you can do the rest of the maths. Ta-ta, and have a great rest of your life.